The boredom of sitting at home all day is finally caught up to you. Having exhausted all usual modes of entertainment, you resort to an activity that you have not partaken in since second grade: crafts. And you decide that paper chains seem like a pretty good idea, so you start making loops and linking them together. But these loops get boring pretty fast, and you're trying to get away from boring things. So you think, well, what if I twisted the loop? Now this makes a much more interesting shape and fancier paper chains, so you're pretty happy. And then you wonder if you could speed up the construction of loops by making two at once. Unfortunately, you cannot link them together after this, but they are still pretty cool. And then you decide to cut one of the twisty loops in half to make more of them too. But this doesn't turn out quite as expected. Today, as you might have guessed, we're going to be talking about Mobius loops. What is a Mobius loop? I'm so glad that you asked. A Mobius loop is the shape that you get when you take a strip of paper, give one end half a twist, before taping it to the other end. A Mobius loop is an interesting mathematical shape because it only has one side. I can take a pen and draw a line all the way around, covering the entire loop, without ever lifting it off. A Mobius loop also only has one edge. This means that it has a special mathematical property that we call non-orientable. We can't define an inside or an outside because they are actually the same. Okay, let's take another look at cutting the Mobius loop in half. I'm just going to take my scissors and make a little slit in the middle of the loop and cut all the way around. Again, after we meet our previous cut, we only have one loop. Another question we can ask is, how many twists does this new loop have? Here, one twist is 180 degrees, so half a rotation. To count the number of twists, we can push all of the twistiness to one half the loop and then untwist that side. It takes 1, 2, 3, 4 twists to untwist this half, so our new loop has 4 twists. First, let's think about why there is only one loop instead of 2. I'm going to draw just the edge of our Mobius loop. We know that the inside will come around and connect to the outside, and the outside will come around and connect to the inside. Now we can imagine making this edge thicker and thicker until it is the width of half the Mobius loop. When we start with a Mobius loop and cut it in half, we just end up with this thick edge. In other words, we get only one loop after cutting the Mobius loop in half because the Mobius strip only has one edge. I found this ribbon with Velcro on the ends that can help us visualize what happens. We can attach the ends together as a normal loop, or if we give one of the ends a twist, we get a Mobius loop. Now, let each of these ribbons represent one half of the loop. We're going to pretend that they're stuck together right now, so bear with me. We can take this end, twist it, and then attach it to the other end of the strip. The red half comes around and attaches to the blue, and the blue half comes around and attaches to the red. So we get one loop as we have discovered before. Again, we can push all of the twistiness over to one half and then untwist it. Four twists, just like last time. So the fact that we only get one loop makes sense now, but where do the 4 twists come from? It seems like there should only be 2. The blue half is twisted once before being attached to the red, and the red half is twisted once before being attached to the blue. This gives 2, right? Well, the large loop made of both halves wraps around the original loop twice. So what happens if we take a loop and wrap it around twice without twisting it at all, or without any local twists? After pulling it open, we see that it actually has two twists, even though we never twisted the strip locally. So the larger loop accumulates the extra two twists purely from going around twice. To recap, we have one twist from the blue half, one twist from the red half, and two twists from going around twice. This leaves us with 4 total twists in our final loop. So you're pretty satisfied with cutting a Mobius loop in half, but another question piques your interest. What happens if we cut a Mobius loop into more than 2 pieces? Well, I'm so glad that you asked, because the next thing that Mobius loop enthusiasts like to do is cut a Mobius loop into thirds. So instead of cutting it right down the center, we'll cut it a little bit off, so we can get more than 2 pieces. Once we make one full circle, we actually end up on the other side of the strip. This happens because of the fact that the Mobius loop only has one edge. If we keep on going, we reach our original cut, and whoa, what? How did that happen? We end up with 2 loops linked together? Okay, there has to be a story here. Let's go ahead and draw some pictures of what's happening. Here we have one Mobius loop that we're cutting in half, and another that we're cutting into thirds. We can compare the distance from the outside of the strip to the first cut. When we cut the strip in half, this distance is 1/2. And when we cut it into thirds, this distance is 1/3. Now, imagine taking the strip that's being cut into thirds and making the distance from the cut to the edge closer to 1/2. We get a skinny piece right down the middle of the strip. This becomes the smaller of the 2 links once we finish the cut. You can imagine that as this distance gets closer and closer to 1/2, the smaller link vanishes. The larger link, which is the outside of the original strip, never changes shape. This tells us that the larger link is actually the same as when we cut the strip in half. Namely, it has one loop with 4 twists. Now, think about changing the distance from the outside to the first cut in the other direction. If we make it super small, then we are just cutting off the very edge of the Mobius loop. As the distance gets closer and closer to 0, the bigger of the 2 loops vanishes. When the distance is 0, we end up doing nothing at all to the Mobius loop. So the inside strip becomes a smaller version of the whole Mobius loop. So when we cut the Mobius loop into thirds, the outside is the same as cutting the loop in half, one loop with 4 twists. And the inside is the same as doing nothing, one loop with 1 twist. But we still don't know why they're linked. The loops are linked together because the edge of the Mobius loop goes through its hole. To understand this, let's look at a picture. Here we have a Mobius loop. Think of this as the inside part of the strip when we cut it into thirds, or the smaller of the 2 links. I am color-coding parts of the edge to make it easier to follow. Now we will imagine taking the larger link and gluing it back on, so uncutting the Mobius loop. We'll start by following this black side around. We have to go underneath the loop at the twist because the black side goes underneath the blue side. Now we've reached our starting place, but this time we're on the blue side. If we keep on following it, when we get to the twist, we have to go over because the blue side goes over the black side. The outside loop, represented by this red line, has to go under the green loop in one place and over the green loop in another. This means that the larger link goes through the hole of the smaller one. This idea might be easier to see in 3 dimensions rather than 2, So I've made a physical model of what we've done here. I've taken a normal Mobius loop and colored the edges in the same way that we had in the drawing. We're going to use a ribbon to represent the bigger link, and pretend to glue it back onto the Mobius loop. Starting with the green part, we'll go all the way around once. Now we're moving into the brown region. In order to keep on following the brown side, we have to pull the ribbon through the hole in the Mobius loop. Once we reach our starting place again, we connect the two ends, and now we have two loops linked together. Those are just some of the visual ways that I think about what's happening, but I encourage you to explore the intuition for yourself. So at this point, you're pretty happy with what you've learned. If you cut a Mobius loop in half, you get one loop, and if you cut it into thirds, you have two loops that are linked together. So, content that you've figured out the mysteries of the universe, you go back to making paper crafts. And you decide that you're going to make even more twisty and pretty Mobius loops by adding more twists. But this doesn't turn out quite as expected. It seems that as you add twists, the shapes get more and more complicated and harder to decipher. What exactly is the pattern here? These shapes that are formed by cutting a Mobius loop with end twists in half are called paradromic rings. Whenever we have an ordered, repetitive action in math that generates a sequence of things, there is almost always a pattern. So what's the pattern here? Well, first we can count the number of pieces that the ring has. For 0 twists, we get 2 disconnected pieces. For 1 twists, a normal Mobius loop, we get 1. And this alternating pattern continues. In terms of twists and knots, this is harder to make sense of, but we see that they increase with the number of initial twists. We can understand the pattern in the number of pieces right now. Here I have a strip of paper that I've colored. One side has this thick gray line, and the other doesn't. And one edge is orange, and the other is green. When we connect the two ends together without a twist, we see that all the colors match up with each other. This tells us that the strip with 0 twists has 2 sides, gray and yellow, and 2 edges, orange and green. Now we'll give this strip a half twist. The gray side matches up with the yellow side, and the orange edge matches up with the green edge. This tells us that a loop with 1 twist has 1 side and 1 edge. If we keep on trying different numbers of twists on our strip, we notice that when a loop has an even number of twists, it has 2 sides and 2 edges. When a loop has an odd number of twists, it has 1 side and 1 edge. The number of pieces in a paradromic ring is directly related to how many sides and edges the loop had before it was cut. Okay, so this first pattern makes sense. But what about these other, more confusing ones? Well, to understand those, we have to talk about something seemingly unrelated. Torus knots. A torus knot is simply a knot on the surface of a torus. What is a torus? Well, have no fear. You already know what a torus is. A torus is simply a donut shape, a shape with one hole. You interact with tori every day, from your coffee mug to your toilet paper roll. We will use this roll of tape as our torus for today. To make a torus knot, we can take a ribbon and wrap it around and through the torus. You can do this however many times you want, as long as the two ends meet in the same place. A PQ knot is one that goes through the torus P times and around the torus Q times. Here I've wrapped the ribbon through the torus 4 times and around once. These numbers uniquely determine the knot, so here we have a 4-1 torus knot. Let's look at a 4-2 torus knot. We're going to wrap it through the center 4 times and around the outside twice. Each time we go around the torus, we go through the middle 2 times. This means that after one traversal, we've made a 2-1 knot. And if we keep on going, we make another. In this way, the 4-2 knot can be reduced to 2 2-1 torus knots linked together. Let's see that again. We start by going around once and through the middle twice. Once we make a full traversal, we've made a 2-1 knot. If we do the same thing again, we make another. These 2 knots together form the 4-2 torus link. If we pretend that the torus vanishes, we see that these 2 links are actually entangled with each other. To generalize what happens here, when P and Q share a common factor other than 1, the knot reduces to a link of multiple knots. We call this a PQ torus link. So why are we talking about this? What does this have to do with Mobius loops? Well, are you ready for the big reveal? It turns out that a Mobius loop with n twists cut in half creates an n2 torus knot or link. This means that if we cut this loop with 3 twists in half, we would get the same shape as if we wrap this ribbon through the tape 3 times and around twice. Isn't that just bizarre? They seem like completely different things. Well, if we put in a little thought, we can understand this equivalence intuitively. First, let's talk about the 2. Notice that when we cut a Mobius loop, the resulting shape goes around twice. If there is an odd number of twists, we end up with 1 loop that wraps around twice. If we have an even number of twists, we have 2 loops that each wrap around once. So cutting the strip into 2 pieces corresponds to wrapping the ribbon twice around the torus. Whether we connect the ribbon at the halfway point or not depends on whether n is even or odd. Now, what about the n? Well, remember that a twist in the Mobius loop corresponds to half a rotation, or 180 degrees. But going through the center of a torus corresponds to a whole rotation, 360 degrees. So in the Mobius loop, the resulting shape goes around twice, and each time makes n 180 degree rotations. This corresponds to the total n 360 degree rotations in the torus knot. So because we go around twice, we double the twists. When I first learned about this equivalence, it really amazed me and I had a hard time understanding what was going on. But through playing around with some torus knots and reasoning through what was happening, I began to see the connection. So I encourage you to grab the nearest torus, preferably not a real donut because those are better for eating, and a length of ribbon, and play around with this for yourself. How can you convince yourself of this equivalence? There is no better time than the present for mathematical exploration. Okay, thank you guys for watching. I hope that you enjoyed this fun video. Make sure to give it a thumbs up and let me know your thoughts in the comments. Until next time, keep exploring.